Okay, so this video is for week 12 of CEP 650. We're talking about autosomal dominant interstitial kidney disease. Um, I received great feedback from one of the students that it would be great to have videos to have me go over the whole presentation during the video, so I'll start doing that as opposed to just about the genetic part. That's fine by me. So let's do it. So obviously the first two slides are just please notice notes, and then we have the title, which in this case we're going to discuss this week only one disorder, so it's going to be relatively less materials, and of course another name used for this is MCKD, medullary cystic kidney disease. So in general, this disease is often misdiagnosed. If you've noticed, we've had more than a fair share of conditions that are misdiagnosed because they have similar symptoms to something else, and when it has a genetic background, the physicians don't always have the tools to deal with it, so they go to what they know. And it's expensive to have genetic analysis or genetic tests done, so it's never the first option. So yeah, misdiagnosed definitely. So MCKD has similar symptoms to that of polycystic kidney disease and or end-stage renal disease, which is a more common diagnostic. The disease causes the kidneys to shrink and become dysfunctional. And if you look at the first photo, you can see that the one right here, so this is my left side, right? This is my left side. Don't be confused by the video that is showing you the opposite. This is my left side and this is the right side. So if you're going to look at it yourself, the shrunken kidney would be on your right side and the normal kidney will be on your left when you're looking at the photo. So you can see a difference in the size of the kidney, in its livelihood, and so on and so forth. And it's obviously more apparent in the presentation than in the photo. I understand that. The disease is chronic and progressive, meaning it gets worse. And then we have two kinds, we'll actually see three kinds, but we have two major kinds and subkinds to the disease. Type 1 symptoms appear at age 60, which, you know, I've been thinking about that. That's kind of weird. I mean, we do think that symptoms should appear due to age. Wait a second. Oh, sorry, I'm a bit under the weather today. That might happen again, just in case you were wondering. So we usually think that symptoms start because of age. In this case, it's a disease. It's a genetically based disease. And then the second one, the symptoms appear earlier, around age 32. It can also be 28, so, you know, give or take a bit. So we're talking about two types of MCKD. Both are inherited in an autosomal dominant manner or inheritance pattern. I want to stop for a second and say again what is constantly in the background of what we're doing. We can differentiate mainly three ways of, or three aspects to be accurate, of inheritance. One is autosomal versus sex chromosome linked. That would be either X linked or Y linked. Okay? In the autosomal inheritance, it has nothing to do with sex chromosomes. It has nothing to do with the sex or gender, sex mainly, biologically, of the parents. and that always naturally leads to a 50-50% of the chances of having the disease between males and females. Okay? Then we have disorders that are X-linked or Y-linked. Vast majority are X-linked. And then we have the whole game, so to speak, the whole dynamic between who makes a carrier and who passes on the disorder or the disease or the syndrome. In that case, usually because a father has one X chromosome and one Y chromosome, which would create a male offspring, right? If it's passed on, then the father makes his daughter a carrier and makes his son the diseased person. Actually, the mother is making the son the diseased person, or the person with the disease, I should say. No offense to the people, to the persons. So we need to have that in your head, because that's going to reoccur again and again and again. And then the second aspect of the game, so to speak, is this trait, in this case it's a syndrome or a disease, the mutation, recessive or dominant? When it's recessive, it's weaker, meaning that one copy of a damaged gene will not create an offspring, or not lead to an offspring, to a person, to a next generation with the condition, disease, syndrome. So you need two defective genes, one from the father, one from the mother. Both are to blame. When we're talking about a dominant inheritance pattern, we're talking about one copy being enough to create the problem. On top of that, then we have the game of chances, right? So the natural chances in an autosomal inheritance pattern is 50-50. But if you are in an isolated community, your chances might go, so the ratio, the mathematical ratio goes down, right? Let's say from 1 to 5,000 to 1 to 500. And the chances of having the situation, the condition, syndrome, disease, go up, because you want to be 1 in a million and not 1 in 500 when it comes to diseases, right? So that's pretty simple to understand. So that's basically what we're talking about. That's basically what we're talking about. So just remember that. So as I said, and I thought maybe it would be great to reword that and say that again, and I hope that when you look at the videos, you go over this again and again, and you realize this. We're talking about an autosomal dominant inheritance pattern, meaning that it has nothing to do with the sex chromosomes. Children have 50-50% between daughters and sons to have the disease, and it's a dominant pattern, meaning that it is enough to receive one defective gene from one of your parents, and you will have the disease. Okay? Then naturally, if you take 4 offsprings of the same parents, there is a 50 chance of being a carrier, a 25% of course, chance of being with the disease, and 25% of not having the disease. Okay, so this disorder is naturally or traditionally being considered as a part of a group, a complex of disorders called the NPH complex. We're still to date in the literature and in the world in a phase where we're trying to separate them the best we can, but we're still kind of halfway linked to the past. So that's why NPH complexes and syndromes are sometimes grouped, and in the more advanced literature, such as peer-reviewed articles, you might find them separated. Symptoms-wise, they're very, very close to each other. Very small differences, very fine differences, often not even seen with the naked eye. You have to actually have a biological sample or be able to go into the body, to invade the body, to see those very fine differences in order to give the very exact diagnosis for which one of the group of syndromes or conditions are we talking about. So misdiagnosis is very simple in this case. The differences are at the histopathological level, meaning at the level of the cell and tissue, mainly tissue in this case. MCKD and NPH are often addressed as one, as I said, though they're not exactly the same. They're usually set apart by the age of the symptoms of onset. We're talking more about childhood and adolescence in regards to NPH, and adulthood and MCKD, respectively. Okay, so the first point on the next slide I already talked about. MCKD has also been referred to as autosomal dominant interstitial kidney disease, abbreviated ADICD, trying to emphasize, in this case, the exact location of where the differentiation of the symptoms is going to come from, and in this case it's in the interstitial space of the kidneys, of the nephrons. When we talk about MCKD, it includes the word cyst. In 80% of the cases you'll find those cysts in the system, in 20 you will not. So it's not necessarily a symptom that you can definitely diagnose according to. So that's important for clinicians, of course. We're not the ones diagnosing this, so this is just an FYI, of course. Oops, sorry. So there's a subtype of type 2 that is often referred to as the juvenile form, actually known as UAKD, so it's uromodelin associated kidney disease, or familial juvenile hyperuremic nephropathy, FJHN, because it's frequently associated with abnormal high levels of uric acid in the blood. But by the way, this is not a unique symptom to this condition. Often problems in the kidneys result in high levels of uric acid in the blood. In this case, we can have dominant mutations in the REN gene. The REN gene has a role to play in the genetic regulation and expression of genes that take part, have a role in the renin-angiotensin system. And they have apparently a tendency to pass through families, so obviously a family history in this case um, is relevant. Then they've been described as associated with anemia, progressive kidney failure. Obviously, I mean, what is the well, I was going to say ultimate, but I guess that's the wrong word, isn't it? What is one of the obvious outcomes of a system that is failing? System failure. In this case, it's kidney failure. Obviously, exactly like we have heart failure, in this case, we'll have kidney failure, right? And then we have fibrosis, meaning scarring of the interstitial space of the kidneys, and this is the most unique symptom for this condition. And then these this subform of FJHN can be categorized accordingly as MCKD or ADIKD. I'm guessing you can tell that I'm under the weather. I'm completely, I'm not feeling so well. So that's that. Then we can go over common symptoms. There's a very long list of them, in case you didn't notice. I think I taught you that when you mess with the renal system, you're asking for it. So we can talk about excessive thirst or excess drinking. That's because the renal system obviously has an immediate and potent influence on blood pressure, reabsorption of water, and the general status of fluids in your body. So the loss of water through the kidneys that are not functioning are going to cause you to want to drink more. Then you might lose, wait a second, sorry. It's just crazy to start recording every time that I need to sneeze. You'll never get a video in your life. At some point, the symptoms might include the loss of control over urination. I just want to say that these are common symptoms. They're possible symptoms. They don't all have to appear. They can appear in different combinations, of course. When you're short on water, obviously you're going to feel weak. Water is a cardinal part of a normal and alive cell and tissue. Anorexia, definitely you can lose your appetite and lose weight as well. One of the unique symptoms that can be caused is pruritus, which in simple English is itching, the need to scratch yourself. So you might have a constant or chronic itch. Pallor, nausea, nothing new or exciting here. Pain, especially coming from the bone. We do know that the kidneys are in charge of the balance of calcium and phosphate, and in this case, calcium lost from the bones will A, contribute to that weakness that we talked about, and B, result in pain. Anemia, the kidneys are also in charge of the balance, or, okay, they're not in charge, but they influence greatly the balance of furin in the body through the hormone PTH. PTH has a linear relationship with calcium, which has a linear relationship with phosphate and furin. So they're kind of all mixed together there. In that case, you might have an anemia that influences the content of furin in hemoglobin, and by that, of course, affecting the red blood cells. Cerebral cortical atrophy, basically tissue injury due to the lack of different substances that the kidneys are not reabsorbing in this case. We know that it can be it can be multiple problems, but most likely ionic based. Then we have obviously one of the major, not one of the major symptom of kidney disease, which is decreased filtration rate of the glomerulus, which is basically the nephron, which is in the center of the system, of the renal system. A bit more symptoms: elevated serum creatinine due to muscle breakdown, definitely one of the symptoms that you'll see. Then we, of course, like with every cell injury or tissue injury, as we have studied, by the way, in CEP 518, pathophysiology, when you don't have complete healing, you're going to have fibrosis or sclerosis, scarring of the glomerulus, and scarring means loss of function in that specific area. One of the symptoms is gout, which is, by the way, treatable and manageable these days. So it's not nice, but it's definitely that we can take away today with medicine, with modern medicine, the symptoms almost completely, if not completely. Then one can suffer hypertension or hypertension. Obviously, it depends where the imbalance of the system, the renal system, is going to, and what kind of hyper or hypo reaction you might have. Impaired renal uric acid clearance. Obviously, the system is not working at its best. Just a few more symptoms, if you don't mind. What a delight to have this disease, or not. Then, of course, an optional symptom, which is basically one of the differentiations of the disease, is the cysts in the small medullary renal area. Then you can have atrophy of the cortical area of the nephron. Then you can have cysts in the area, in the connection between the two areas, the cortical medullary area of the nephrons. Then you can have renal hypoplasia, meaning the destruction or the decrease in tissue and in cell count, right? You can have renal salt wasting, which is very bad when you look at it from an ionic standpoint. Ionic standpoint always will influence electrical conductance. Then, of course, it can result in stage 5 chronic kidney disease, which is a very advanced level of kidney disease. Then you can have atrophy of the tubulus, which is very important for the filtration part of the nephrons. You can have a separation of the basement membrane of the tubules, basically leading to mechanical instability, which doesn't work well for cell function, right? Then you have fibrosis in the interstitial areas between the tubules, and then nephritis, which is an inflammation of the nephron. So, did you notice for the first time I used an emoji in one of my presentations? That is part of my evolution as a professor. I'm not sure I'm going forward or backwards in this case, but I thought it would make you laugh. Hopefully. Alright, diagnosis. In this case, genetic testing is definitely the most accurate way to diagnose, which is problematic, obviously, because it's costly. It's not used as a first option, but it's the most accurate way. Other ways are, that also elevate the chances of misdiagnosis if they're the only one used, because they're not going to produce a unique symptom just for this condition. Is blood test serum creatinine, blood test uric acid, and a kidney ultrasound. Once again, those are not sensitive enough to give a accurate diagnosis. A few more general ideas in regards to the group of complexes. So you see that NPH occurs during childhood and progresses to renal failure before the age of 20 years. So that can be, although at age 20, you'll have renal failure, which is horrible. But the age in this case is one of the ways that we can, in a non-biological way, differentiate between the conditions. Then we see that the median age of onset of ESRD is 13 years in juvenile NPH and 1 to 3 years in infantile NPH and 19 years in adolescent NPH. So basically, that's the part that explains the first bullet, which is before 20 years of age. I do want you to remember the ages that it occurs and the definition. So which one would be infantile, which one would be adolescent, and so on and so forth. Usually if ESRD, end-stage renal disease, has not developed by the age of 25, we can have another diagnosis which is called recessive NPH, but that is unlikely. And then so it's a possibility, it's just unlikely to happen or to be the correct diagnosis, and that's why usually the diagnosis will go to MCKD. Alright, let's start the genetic information part. So the incidence of juvenile NPH is 9 cases per 8.3 million. That is a very rare disease. Very nice odds, better than some that we've seen before, right? And then we see that nephritis is the most common genetic cause of ESRD in the first 2 decades of life in case of juvenile NPH, accounting for 5 to 15% of all of the cases of people with ESRD, so not only with this condition. The disease is rare, as you can see, and its highest prevalence is actually in the US, which is interesting for 2 reasons. A, we have a relatively isolated community in the US, but on the other hand, the US is 300 million people, and it's quite huge. So on the one hand, something here, maybe lifestyle, maybe the genetic pool here is causing a higher prevalence, meaning the odds here are worse than in the world. On the other hand, you can't say that the US is exactly an isolated population. It's not a small population. I mean, when you say 300 million, that's not isolated. So, and interesting, very interesting. We don't know why exactly the highest ratio is in the US. So approximately 200 families with MCKD type 2 have been reported, each one of them having several affected individuals. Then we see that the incidence or the occurrence of NPH in Europe is higher, when it accounts for 15 to 25% of cases in ESRD during childhood. Okay. No racial prediction is noted. Both sexes are equally affected because it's autosomal and not X or Y linked. I explained that before. And they're both MCKD types are inherited in a dominant pattern. Once again, you only need one defective copy from one of the parents to have the disease. And then we see the chances of passing the disease to one's children, which we have talked about. Going a bit more into the genetics of it, we see that we have mutations to several genes that have been associated with the condition, at least 4 by the way, and there's more and more that are being found. The first one is the MUCHIN1 kidney disease, MCKD mutation within the MUC1 gene, which is located on chromosome 1. That's why it's MUC1. And this mutation in this specific gene rarely causes the cysts. So this is not a cyst-causing gene. The second type is due to mutations named UMOD to a gene called UMOD. That's the eumodelin one that we talked about on chromosome 16. That encodes for a protein called eumodelin. Type 2 obviously often leads to gout. So we do have what we call here, and we've seen this before by the way, a genotype-phenotype relationship. So for instance, we have a negative or a reverse genotype phenotype relationship when it comes to MUC1. We know that it does not usually causes cysts, and then we do know that mutations to the UMOD gene leads usually to gout as a symptom. Then we see that adult NPH is caused by mutations to the genes NPHP1 and HP2 or INVIS, and the juvenile one caused by the NPHP3. One thing I want to tell you is that we do know that there are mechanisms that regulate the timing of expression of genes. How do we know this? We know this because we know that certain phenomena happen at birth. I'm not talking about diseases, by the way. Normal phenomena, normal traits, right? Proteins appear at certain ages of life in order to allow certain abilities. So for instance, we have genes expressed at birth. We have genes expressed only during adolescence or childhood or adulthood. So it's more than likely that there's some kind of timing mechanism that causes NPHP3 to be expressed and cause, and if it's mutated, to cause the juvenile form, as there is a timing mechanism of sort, which we don't know, by the way. Once again, we don't know the mechanisms. It's one of the greatest things that we're still trying to look at, for and find when it comes to genetics, that will cause mutations in the other genes to be expressed later on. So that's additional information that I don't think I've ever taught you before. Let's see. Okay, we talked about that. And then we see that a very interesting type of mutations is causing these conditions, and that is a single nucleotide insertion which is rare. It's not the usual way of causing the worst syndromes. So obviously that means that one nucleotide is added, only one nucleotide is added to the whole polypeptide chain. Okay. Functional and practical implications. The mutations affect the cilia of the renal system. Cilia cells, as you know, are used not only in the renal system. It's an idea, a principle of how the cell works, and in this case, we also have cilia in the kidneys. Cilia are great for mechanical feedback. They are great for sensing mechanical pressure and mechanical forces, and through that also flow, all kinds of flow. So we have cilia in different areas of the body, and they definitely have baroreceptors, mechanoreceptors on them that allow us to understand what are the forces working within the system according to how they are influenced to bend forward. So changes in tension help the feedback. So those are very important cells that definitely influence in a cardinal way the feedback and regulation of the renal system. They are cardinal to the system, to the function or the normal function of the system. Then accordingly also it affects the secretion of growth hormones affecting the kidney. So if you have an abnormal feedback loop, you're going to have an abnormal growth rate. Okay? We see that the NPHP1 gene affects cell-to-cell signaling, affecting the tissue's integrity, meaning that the cells are not communicating accurately between themselves, and then you kind of lose, in a way, the idea or the communication basis to a tissue. A tissue is a group of cells that are communicating and acting as one, in a way. We see that mutations to NPHP2 or INVEST develop defective cilia and cysts. Same idea, nothing new here. Okay, so basically, once again, the major mechanism of which these mutations affect the system. They affect the cilia cells and the communications between the cells. We lose accurate control of mechanical feedback, and we lose by that regulation of the system, and that leads to all the symptoms that we were talking about. More practical implications. Mutations to the NPHP3 gene cause a more wide variety of symptoms because they influence more areas of the system. They influence the primary cilia, they influence the basal bodies, they influence the centrosomes, okay, or the mitotic spindle of the cilia. So they're affecting more aspects of the nephron than the other genes. Usually when a gene is more central or has more effects, then a mutation will cause more symptoms. We've seen that before in prior conditions. Then we see that the UMOD, the mutations to UMOD affect the watertight integrity of the nephron segment, meaning, or translation to English, so to speak, from biogenetics language to English, it affects the tight relationship between the nephron and its ability to absorb or release water. Okay, we see that in the MCKD type 2 condition, the mutant remodeling proteins cannot exit the endoplasmatic reticulum, and that means that they are accumulated in an abnormal way within the ER of the cell. I want to remind you that there's not enough space in a cell. It's not endless. So when you're accumulating proteins, A, if they're reactive, they might react with something in the cell. B, they are literally taking up space, and that will lead to dysfunction of the cell. It might make the cell explode and die because it's simply going to accumulate until the membrane can't take the pressure. So you have an increased pressure within the cell. So at the end, it's going to lead to cell death, and cell death means that the cell is going to die and shrink, right? So current treatments, there are no specific therapies for the disease itself. We're talking about a group of diseases, so you can expect similar therapies or treatment to that group. We can treat anemia with erythropoietin. We can use growth hormone if we have a hyposecretion of growth hormone or a lack of effectiveness of growth hormone on the cells in order to have them not shrink and not die, right? Most likely renal transplant, kidney transplant is going to be needed at some point because we have the tissue and the organ dying. We want to lower phosphate and potassium diet. We have different medications for gout. One of the more common one is allopurinol, but there's others. It's not the only one used. Then we can have ACE inhibitors for the ADT-KD or the MUC1 and the REN type of mutations, and we know that any problems in the renin system, people with problems in the renin system should avoid non-steroidal anti-inflammatory agents. Future possible treatment. Couldn't find any new treatment that is more than just trying to achieve a more effective outcome to the treatments that we have already. It is indicated clearly in the literature that the treatments are getting more and more effective for the symptoms. There have been very few trials of inducing a deletion mutation that would delete the insertion. Usually that's supposed to be easier, but they have not been. They've been successful in vitro, not in vivo. There's not much trials going on because, as I said, this condition is often misdiagnosed. Exercising. There's quite a bit about the idea of exercising these people. Basically, in theory, they are addressed as people with renal failure or chronic kidney disease, even before renal failure, right? They tend to be inactive normally and have reduced physical functioning and performance. Exercise is definitely advised for them. we see that aerobic exercise interventions have been shown to increase maximal oxygen consumption in selected patients, meaning it does not affect 100% of them. It definitely depends on the severity. And of course, it's improving the situation, but these people are diseased, so it's not going to be, the capacity is not going to be of a normal person. There's kind of mixed information. I've read a few articles. I thought they were interesting, so I read them all. Actually, there's not much, but whereas a combination of aerobic and resistance training manipulation did improve blood pressure control and lipid profiles and mental health. In some cases, and in others it didn't. So that was a bit interesting. Once again, there's not the problem with this population is that there's not a lot of them specifically diagnosed with this condition, so the sample size is relatively low, and then personal traits might interfere with, the significancy and the statistical analysis of conditions. There are a few larger studies showing that aerobic training can also improve physical functioning and performance. Nothing new about that. I mean, what else is going to improve if not that? Then we can talk about resistance training, increasing muscle strength and size, and may also improve functioning, meaning they didn't find a 100% correlation between the two. So the last point is that the studies conducted up to date have either aerobic training or aerobic and resistance training, but no one thought of just doing resistance training on physical functioning. There's a reason for that, by the way. There's several diseases and syndromes that you'll see those studies not have a group where resistance training is the only thing that is conducted, especially if the past shows that aerobic exercise has a positive influence on the symptoms and the conditions. You might have an ethical problem with denying subjects treatment. We've talked about exercise as medicine, right? Exercise is part of the treatment, should be part of the treatment. So are we allowed as researchers to deny someone, even for one day, possible treatment that might, save them from death, might save them from the progression or slow the progression of their disease? And that's why often we don't see just resistance training being one of the manipulations of the study, although it should be as researchers. So that's what I have for you for this week. I hope you study well for the exam. Please, 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 please contact me if you have any questions about the materials for the exam. Okay, don't get to the exam and then not understand what's going on. Obviously, I won't tell you exactly what the questions are going to be, but I can tell you what to focus on. So, if anything regarding the genetic part of it, which is my main focus usually, which is usually in the heart of the, in the center of the question, contact me. You're second year students. You're not shy. There's no reason not to ask. There's no reason not to answer. Have a great day. Bye.